Alright, in this video I would like to talk about alternating series tests. So this is a special class of series that looks something like this, where we have a negative 1 to the n or a negative 1 to the n plus 1, so that the signs of each term of the series alternates, and hence the name. Alternating refers to the signs. So what the alternating series test says is that if these a sub n terms are positive, right, they have to be positive so that this will actually change the sign, because if the a sub n start changing signs, then we could end up with some kind of a random pattern of signs. What we want is every other term to be positive and every other term to be negative. So really the only difference between these two is this one basically guarantees that the first term will be negative, since the a sub n's are positive, and the negative 1 to the first is negative 1. Where here, our first term of the series would be positive. But in either case, whether it starts off negative or positive, both of these types of series, I should say, would converge if the limit of the a sub n's goes to 0, and basically the a sub n's are monotone and decreasing, right? So they're, as you go farther and farther out, the terms, again, remembering these are positive, the terms get smaller and smaller, or at the very least stay the same, right? So this one in particular, I should point out. This is the one that, I think many times students are tempted to say that any series converges if this is true, and that is not the case, right? We saw an example with 1 over n, right? The harmonic series from n equals 1 to infinity. This diverges, even though the limit as 1 over n goes to 0. However, what we'll see here is that for the alternating harmonic series, it converges because it satisfies this. So I guess we're jumping down to the first example, right? What we have is, first, the limit as n goes to infinity of 1 over n clearly equals 0, all right? But we already know that that's not good enough to make it converge unless we have alternating, right? So that alternating piece. The other part then we need to check is this: 1 over n plus 1 is certainly less than or equal to 1 over n. But it's the alternating piece that makes the alternating harmonic series converge, where the regular harmonic series diverges, because we have this cancellation with the positive and negative terms each time. Enough cancellation takes place so that this one, the alternating harmonic series, converges. All right, and we'll come back to that a little bit later in the lecture. We have this thing where if you don't have it alternating, it diverges, but if you do have it alternating, it converges. We call that conditionally convergent, and we'll talk about that a little bit more later. Let's just look at a couple more examples here of applying the alternating series test. So in this second example, again, we have two things to check. And remember, the a sub n is just this part of it, right? It's just the part that's not alternating. So what we need to do first is take the limit as n goes to infinity of n plus 1 over n. And clearly, we can take the ratio of the leading coefficients. We can see that that limit equals 1. So it does not satisfy this. And in fact, this is our nth term divergence test. If the limit of the terms doesn't go to 0. So what we said was, if it converges, this would be true. And this is talking about for series that aren't alternating. We said if the series converges, this is true. But if this is not true, then automatically we know the series diverges. And so that's what we have going on here. We don't even need to check the second, although it's true for the second. So I'll just kind of point that out, that if we replace n with n plus 1, we end up with n plus 2 over n plus 1. And that is true. But it doesn't matter, because this one means that it diverges. Okay, how about we take a look at the next one? So here, let's take a look first at the first thing. So let's kind of point out the pattern going on here. It's going to be hard to write as a formula, but I have 2 over 1 minus 1 over 1, plus 2 over 2 minus 1 over 2, plus 2 over 3 minus 1 over 3, plus 2 over 4 minus 1 over 4. So without writing that out as a pattern, I guess we could kind of say we have 2 over n minus 1 over n. And if we take the limit of that as n goes to infinity. Clearly each of those, that's going to be the limit as n goes to infinity of 2 over n minus the limit as n goes to infinity of 1 over n. Well, that's 0 and that's 0, so the whole thing is 0. So we've got that. But the second part we do not have because as we go out, right, if we're just looking at the a sub n's, we're just looking at these positive things, we know that it's not true that 2 over n, right, is less than or equal to, so if we look, for example, the 2 over 4 comes after 1 over 3, right? So 1 over n minus 1. That is false. So the alternating series test doesn't apply here. It may converge, it may not converge, but we can't say that it converges using the alternating series test because of the second condition is not met. Okay, so that's the alternating series test. So another interesting property of alternating series is that we can estimate the infinite sum using this alternating series remainder theorem. So let's just take a look at this real quick. We have an alternating series, and we know it converges. And so if it converges, that means that this infinite sum adds up to a number which we'll call s. We'll just s for sum. Then the difference between the nth partial sum and the infinite sum, which we're going to denote this Rn. So this is the absolute value of the difference. All right, and we're going to use R sub n to denote the remainder. All right, so the remainder, what's left, the difference between our nth partial sum and our infinite sum, is less than the n plus first term. So let's look at an example of that. For if we look at the alternating harmonic series, here is the first 5 terms of that series. Let's see, here we go. So I already did the work. I'm not going to go through all the gory details, but if we add those all up and approximate them using a decimal, we get 0.825. And we'd like to know how close that is to the infinite series. So this is just S5, all right, the 5th partial sum. How close is that to the infinite sum? Well, we can determine S minus S5, all right, so that's in this case, our n is 5, and we're going to call that the remainder of the 5th partial sum, and that would be less than or equal to a 6, right? When we know the next term in the sequence is 1/6, which is 0.166 repeating. All right. So what this tells us is that the infinite sum will be greater than or equal to 0.825 minus 0.166 repeating, and less than 0.825 plus 0.166 repeating. Or, in other words, that it will be between 0.6583 and 0.9917. All right, so that gives us, we can do better the farther we go out. Many times you'll end up with series where the terms are getting small very quickly, and so you don't have to go very far out to get a pretty darn good approximation of the infinite sum. So that's just an example of how this particular theorem works. In the next example, we're going to use this theorem in order to approximate this infinite sum within 0.001 using the so the question is, how far do we go out? How far do we need to go out to Sn? We want to go out to Sn, so the difference between S and Sn, again, we're calling that the remainder, that will be less than or equal to 0.001. But according to this up here, it's also less than, so it's also going to be less than a sub n plus 1. All right. So what we basically want to do is figure out when these are equal. All right. So let's look here. Remember, the a sub n's are just the positive part of this. We don't really look at the alternating part. So a sub n plus 1 is 1 over n plus 1 to the fourth, and we want to know when that's going to be equal to 0.001. All right. Well, I'm just going to rewrite that as 1 over 1,000, because then it's clear to see this will be true when n plus 1 to the fourth equals 1,000. So if I take the fourth root of both sides and then subtract 1, n would equal the fourth root of 1,000. That would just give me n plus 1, and then I subtract 1 from both sides. Well, that turns out to be 4.62. But of course, n has to be an integer, and so we can't go down. We can't go down to a4. We need to go up to, in other words, we need to round up to 5. Okay, let's see, get this all on the, here we go. Round up to 5. So what we want, so S4, so it'll be less than, if we, A5 is what we want here. So what that means is, since 5 is n plus 1, then S4, which would just be the sum from n equals 1 to 4, negative 1 to the n plus 1 over n to the fourth, that will approximate the infinite sum, S, within 0.001. All right. So again, this is just a way for us to use the theorem to see how many terms of the series we would need to get a certain desired level of accuracy. Okay, last thing I want to talk about with alternating series is something I alluded to at the beginning, is this idea of absolute and conditional convergence. So I'm gonna talk about that. I'm going to begin talking about that with an example. So here we have a case. We know that sine bounces between negative 1 and positive 1. And so if we were to look at the terms of this, which would be, they would look like sine of 1 over 1 squared plus sine of 2 over 2 squared plus sine of 3 over 3 squared, and so on. We know that some of these sine terms will be negative, but it's not necessarily alternating. So the alternating series test doesn't apply. So how can we wrap our heads around or determine whether or not that particular series converges or not? Well, one way to look at it is that if I take the absolute value of this, since we know that sine of n always bounces between negative 1 and 1, then an absolute value is always going to be between 0 and 1, which means every term of this series will be less than or equal to 1 over n squared. All right. Now, we know that this series, if we were to write it as a series, n equals 1 to infinity, we know that converges because it's a p-series with p equal to 2. All right. So what that tells us is, by comparison, that this series converges. But note, that's not the same series that we started with, right? So we know this converges by comparison with this p-series. But what does that tell us about the original? All right. So we have this idea of absolute convergence, which will answer that question. All right. So absolute convergence says that if I take the infinite series of all the terms in absolute value and that converges, then the original series will also converge. And I think intuitively this makes sense. This is basically making all of the terms positive. And if all the terms positive add up to a finite number, then having some of them be negative and some of them be positive will that's going to end up being something smaller, right? So it makes, you can think of this as by comparison. This is going to be the bigger of the two series. So if this one converges, then this one's going to converge also. So what that obviously tells us about our example is that this converges. And a series with this property, where if you take the series and you take the terms and put them in absolute value and it still converges, we would actually say that this series converges absolutely. Meaning that not only does the series converge, but if you took the absolute value of each of its terms, it would still converge. Let's look at an example of conditional convergence. So conditional convergence means that you would have the infinite series would converge, but if you took the absolute value of each of those terms, that would diverge. All right, and we've already seen an example of that at the beginning here, n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. So we already showed earlier this converges, but we know that without the alternating, just the harmonic series diverges. So this is something that converges conditionally. Conditionally, again, just meaning that without absolute value it converges, but with absolute value it does not. So let's just look at a few more examples of this idea of conditional and absolute convergence. So let's take a look at, we have negative 1 to the n factorial over 2 to the n. All right. So let's, if we look at this in terms of first let's just take a look at the absolute convergence, right? So if we look at n factorial over 2 to the n. So let's not worry about, we know all these terms will be positive. And so if we take the limit as n goes to infinity, what happens here? All right, so it might not be obvious. Let's write out what n factorial means. It means n times n minus 1 times n minus 2 down to 3 times 2 times 1. And what does 2 to the n mean? It means 2 times itself n times, or 2 times 2 times 2, all the way down to 2 times 2 times 2. So the reason I write this out is because the question, if you just look at it, it might not be obvious which one's growing faster. All right, but you can see here, for the first and second term, the bottom is bigger. But after that, all of these terms, right, because these keep getting bigger. So 3 is bigger than 2, and we're going to keep on going up. So the numerator is bigger than the denominator, the numerator is bigger than the denominator, the numerator is bigger than the denominator. So we know that this is not going to go to 0. All right, so in this case, this series doesn't converge either absolutely or as an alternating series, because this fails our first test for the alternating series, where the limit of the terms has to go to 0. All right, one last example I'd like to take a look at. We have negative 1 to the n over the square root of n. All right, so let's apply the alternating series test. First, we look at the limit as n goes to infinity of 1 over the square root of n. Clearly that goes to 0 because the denominator grows without bound while the numerator stays 1. Secondly, we take a look at, is the square root of n plus 1 over the square root of n plus 1 less than or equal to 1 over the square root of n for all n? Yes, denominator is getting bigger, so the reciprocals are getting smaller. So this converges by the alternating series test. All right, but let's take a look at the absolute. So if we take the absolute value, then we're just left with 1 over the square root of n, which we can write 1 over n to the 1/2. And we know that that diverges. It's a p-series test, or sorry, it's a p-series with p equal to 1/2. And we know if p is less than or equal to 1, it diverges. So this is another example of a series that the alternating series converges, but the in absolute value it diverges. So again, we have just another set of series, alternating series, that have some pretty nice properties that we can use to determine whether or not they converge or diverge.